Hi everyone, today a video in the energetics series looking at enthalpy changes. So what we talk about here is something called thermochemistry, thermodynamics of chemistry. And when a chemical reaction takes place, we know that chemical bonds break and new ones are formed. And this idea of thermochemistry allows us to calculate the energy value of fuels, the requirements for industrial processes, the energy needed to be breaking and making these bonds, the energy needed to break a bond or the energy released when a bond is made, and to overall predict if a reaction will actually take place depending on the heat changes. So energy must be put in or supplied to break bonds, and the converse of that is also true. The energy must be given out or released when we form bonds. That's a really key takeaway from this slide, that we have to put energy in to break bonds. Energy is given out when we form bonds. And once we calculate all the bonds that have been broken, all the bonds that have been formed, we'll be able to calculate an overall energy change for that reaction. And it'll either end up being that we've overall had energy being taken in, or overall we've had energy being given out. And this is the energy change for a particular reaction. Now we say that if overall energy has been given out, that is that the products that we've made have less energy than the reactants that we started with, this is what we call an exothermic reaction. This is where we have given heat out. Examples of this include combustion reactions, so burning things, as well as neutralization reactions, so an acid plus a base to give salt plus water. And the other type is an endothermic reaction. This is if we have overall energy being taken in, so our products have more energy than the reactants did. So we've had heat taken in. An example of this would be a thermal decomposition reaction. So for example, calcium carbonate, CaCO3, thermally decomposes to produce calcium oxide and CO2. I haven't heated this like I might have done in a combustion reaction. Here I've had to take energy in order to have this reaction take place. So energy has to be put in to break bonds, energy is given out when bonds form, and if we have overall energy given out, that's an exothermic reaction. If we have overall energy being taken in, that's an endothermic reaction. Now it's always the case that if a reaction is exothermic in one direction, it is endothermic in the opposite direction. And so as long as we know whether it's exothermic or endothermic in a particular direction, it doesn't necessarily have to be forwards, it could be going forwards or backwards. As long as we know one of those directions, the other will just be the opposite. And so if we have going from reactants to products, we have an exothermic reaction, we know that the reverse direction, going from products back to the reactants, would be an endothermic reaction. And so those exothermic and endothermic essentially just swap if you swap the direction of the reaction. And the amount of heat transferred during chemical reaction, the amount of energy that we either take in or give out, remember that heat is just a form of energy, the amount of heat, the amount of energy that we transfer depends on the quantity of the reactants. Obviously, if we start with more reactants, typically we're going to get more energy, more heat transferred during a reaction. And we measure our energy in kilojoules per mole. So the kilojoules is our energy part of it. Typically it's kilojoules rather than just joules because they tend to be fairly big numbers. And then we also take into account how much of the substance we have, because the amount of heat depends on the quantity of reactants. And so we normalize it for a mole of the reactants. So it's kilojoules per mole. And if we're doing these calculations for thermochemistry, it's really, really important that we write out our reactions and we include the state symbols and we state the conditions of a reaction. And so this example at the bottom here is a neutralization reaction. Remember that a neutralization reaction I said was an exothermic reaction. Energy was given out. And here we have sodium hydroxide plus HCl to produce NaCl and water. Now for thermochemistry, it's really important that we don't just write the reaction down, but we also write the states, what these are in. And so we have our sodium hydroxide and our HCl. These would both be aqueous solutions dissolved in water. Our sodium chloride as an ionic salt, but technically would be aqueous under these conditions, dissolved in water as well. And our water is a liquid. And I've also written at the side here that this was done at 25 degrees Celsius, that's the temperature. and also at 100 kilopascals. This is the pressure. So it's important to make sure that we write down what the conditions are, but also our equation with full state symbols. And this then leads us on to something called the enthalpy change. So the reason why I said it's important to write down the conditions is because the amount of energy that we give out or we take in during a reaction varies with the conditions, such as the concentrations, the temperature, and the pressure. Now, when we measure a heat change at constant pressure, we call it an enthalpy change. So an enthalpy change is just a heat change, an energy change like we've been talking about, but it's done at constant pressure. We also have this idea of standard conditions. We'll see that we will refer to something called a standard enthalpy change. And a standard enthalpy change refers to an enthalpy change. Remember, an enthalpy change is just a heat change or an energy change at constant pressure. And we measure it at standard conditions. Now, this is given the symbol delta H. The delta H stands for H is enthalpy. Delta, that triangle shape, is a change, so we have an enthalpy change. 298 just references the fact that it's at 298 Kelvin, 25 degrees Celsius. And then the symbol at the top is indicating that we are at standard conditions. And so the standard conditions are 100 kilopascals, 298 Kelvin, and 1 mole per decimeter cubed solutions. So essentially that is saying that we're at 1 mole per decimeter cubed solutions, room temperature, 25 degrees Celsius, and standard kind of atmospheric pressure, 100 kilopascals. Now, we said that an exothermic reaction was where we gave out heat, we gave out energy, and so the products end up with less heat energy than the starting reactants have, because we've given out heat energy, they've lost heat energy. And so by losing the heat energy, they have heated up the surroundings. And we'll talk about this in a few slides' time, that we have a system and we have a surroundings. Our system is the actual chemical change that is going on. So, for example, the neutralization reaction, our chemical system is the actual HCl and NaOH, our actual reactants. Everything else is the surroundings. So this would be done in aqueous solution, and therefore the water technically is the surroundings. So in an exothermic reaction, the products have less heat energy than the starting reactants. They have lost heat energy. That means that our surroundings have been heated up because energy has been gained by them. And what it actually means is that if an exothermic reaction takes place, it feels like something is getting warmer. So if you do this exothermic reaction, say in a polystyrene cup, you would feel the polystyrene cup getting warmer. And the reason for that is because our products that we've formed have less energy. They've lost heat energy. That heat energy has been absorbed by the surroundings. The surroundings is the water, the polystyrene cup. That therefore feels hotter. We've gained heat. And what this actually means is that our delta H, our enthalpy change, is negative. It's showing that we've lost heat energy. So the delta H refers to the enthalpy change of the system, the actual chemical entities that we're dealing with. And so in an exothermic reaction, we lose heat energy from our system. Delta H is negative. The other example we said was an endothermic reaction. This is where the products have more energy than the starting reactants did because we've gained heat energy. So if we've gained heat energy, what they have been done is they must have been heated up by the surroundings. We must have gained the heat from somewhere, must have gained the energy from somewhere. And so again, we have this idea of our system being the actual chemical entities, our surroundings being everything else. And so if I again have a reaction going on in a polystyrene cup with some water in, the reaction takes place, it's an endothermic reaction. That means our products have more energy than the reactants had. So they've gained energy, but where have they gained it from? They've gained it from the surroundings. So if you do an endothermic reaction, the surroundings will feel cooler because they've lost energy. Whereas the system, the actual chemical entities, have gained energy. So in an endothermic reaction, the products have more energy than the starting reactants, and it means that delta H, the enthalpy change, is positive. And the final thing to say is just not to get confused by all these different terms. A heat change is the same thing as an energy change because heat is just a form of energy. So quite often these are used interchangeably. You might hear people talk about heat changes, energy changes. Typically they are used fairly interchangeably. And an enthalpy change, remember, is just the same as an energy change. The only key bit is that we're doing it at a constant pressure. So an enthalpy change is an energy change, a heat change at constant pressure. And we give it the symbol delta H. And then, as I said, we often refer to a standard enthalpy change because the heat energy given out depends on the conditions. And so our standard enthalpy change is our enthalpy change measured at the standard conditions, and they are 100 kilopascals, 298 Kelvin, and 1 mole per decimeter cubed. So we can now start to look at some actual definitions of some enthalpy changes. And while these definitions may seem a little bit dry, they're really, really important to learn. They're easy marks in an exam if they come up, but they also help you sometimes in calculations to remember exactly what it is that you need to calculate. And so the two that we really need to know, the first is our standard molar enthalpy of formation. We give this the symbol delta HF. The F just stands for formation, and then we have that symbol there at the top, which is indicating that we're at standard conditions. So standard molar enthalpy of formation. And this is the enthalpy change when 1 mole of a substance is formed from its constituent elements under standard conditions, all reactants and products in their standard states. So this could be really the formation of any products. This could be the formation of water from hydrogen and oxygen. It could be the formation of ammonia from nitrogen and hydrogen. It could be the formation of ethanol from carbon, hydrogen and oxygen. It doesn't matter what we form, our enthalpy change of formation is the enthalpy change, the heat change at constant pressure, when 1 mole of the substance, the key thing here is 1 mole, it's a standard molar enthalpy, so it's only relating to 1 mole, of a substance is formed from its constituent elements under standard conditions and everything in their standard states. So the standard conditions, remember, is just the 298 Kelvin, 100 kilopascals and 1 mole per decimeter cube solutions. And when we talk about a standard state, the standard state of an element is the state in which it exists at standard conditions. So that's 298 Kelvin, 100 kilopascal, and if it's a solution, 1 mole per decimeter cubed. And so we just have to think about, well, how does that element exist at room temperature and pressure? How would you normally find that element? So stuff like hydrogen, oxygen, nitrogen, gases, carbon as a solid, for example. And so just think about, normally use your chemical common sense and think about what does that element normally look like. What it also means is, how do we usually find an element? So we don't normally find, for example, oxygen just going around as an oxygen atom. At standard pressure and temperature, we find oxygen going around as O2, dioxygen. The same for hydrogen. We don't really normally find hydrogen going around as just hydrogen on its own. We find hydrogen as H2. So it also refers to that as well. The other one is the standard molar enthalpy of combustion. This is delta HC. And this is the enthalpy change when 1 mole of a substance is completely burned in oxygen under standard conditions, all reactants and products in their standard states. So again, we have an enthalpy change, a heat change at constant pressure when we burn 1 mole. Again, that's that really key idea that it's 1 mole of a substance, because remember, these heat changes depend on the amount of our reactants. So it's the enthalpy change when 1 mole of a substance is completely burned in oxygen under standard conditions, and all the reactants and products in their standard states. And so the final thing to say on a standard state is that it's really, really important to include the state symbols. This is why when we talked about writing our equations, not only do we have to have the conditions written down because they affect the enthalpy change, but also we need to know what's the standard state of our element. So always include the state it's in with the state symbols. We can then draw some diagrams for these different types of enthalpy changes, and these are simply called enthalpy diagrams. So over on the left we have an exothermic reaction, over on the right we have our endothermic reaction. Now these diagrams always look roughly the same in terms of the axes. So going up the y-axis we have energy. Sometimes you'll see it written down as enthalpy. Remember, essentially enthalpy is just energy at a constant pressure. Sometimes you may even just see heat. Again, these are all fairly interchangeable. And then on the x-axis, you have the extent of reaction. So what this essentially means is how far along the reaction are we, from where we start off with just products to starting off with just reactants to ending up with just products. How far along that in between are we? It's sometimes called the reaction coordinate, but it just simply means essentially how far through the reaction are we. And so we can draw very simply lines just to dictate where our reactants and where our products lie on this energy scale. And we know that for an exothermic reaction, we lose heat energy from the system. We give out heat energy from the system. And so therefore our products have lower energy than our reactants did. And so we draw our line for our reactants The line for the products is lower down than it was for the reactants. And we can draw an arrow, a simple vertical arrow that goes from the reactants to the products, going down in this case. And that's showing you that the delta H, the energy change at a constant pressure, the enthalpy change, is negative because we've given heat out. On the other hand, we have our endothermic reaction. So again, y-axis is energy, x-axis extensive reaction. And again, we can draw our reactants and our products as these horizontal lines. Remember, for an endothermic reaction, our products have more energy than the reactants did. We've taken heat energy into the system, we've increased the amount of energy, and therefore we have our products line being higher than the reactants. And again, we can draw a simple vertical arrow that goes from the reactants to the products, this time going up, always goes from reactants to products. And we can see here now, because it goes up, our delta H is positive. Our energy change at a constant pressure, our enthalpy change, is positive because we've taken heat into the system. So an important distinction just to clear up here is the difference between heat and temperature. We've been talking about heat as an energy change. And that's absolutely true. The heat is a measure of the total energy of all the particles present in a given amount of substance. This differs from temperature because temperature is related to the average kinetic energy. And the key thing really there is the fact that it's an average. So it not only depends on the total energy, but actually how many particles we have. Because to calculate the average, we'd have to take the total energy and divide it by the number of particles we have. And so temperature is related to the average kinetic energy of the particles. Now, it's actually independent of the number of particles, something we call an intensive property. Now, this might sound a bit odd given that I've just said it would depend on how many particles we have. The reason why it's intensive, the idea that it's independent of the number of particles we have, is that, let's say I have 100 particles. To calculate the temperature, I have to calculate first the total energy that we have of our particles. So I calculate that amount of 100 of them, and I divide it by how many particles there are, 100. Now, because essentially both the top and the bottom parts of that equation depend on how many there are, obviously the number of particles depends on how many particles there are, but also the total energy because it's just a sum. So the more particles I have, the more the total energy is. And so therefore you'd actually find the temperature would be the same if I took the same system but only had 50 of those particles. While the total energy would be half, also the amount of particles I had would be half of that when we had 100. So temperature is the average kinetic energy and is independent of the number of particles. It's measured with a thermometer. And as we said, heat is our total energy of all the particles present in a given amount of a substance. And so it does depend on the number of particles, something that we call an extensive property. Because we're not calculating an average here, we're simply just calculating the sum, the total of the energy. It does depend on how many we have. If we have more particles, we have more energy. And that's because we have to include every single particle, the energy of every single particle. Now, heat always flows from high to low temperature. And so you can start to think about some examples where these two terminologies differ in quite a big fashion. And so an example would be, for example, to think of a red hot nail, a really small but red hot nail, compared to a lukewarm cup of water, a lukewarm bath of water, let's say. The lukewarm bath of water, while it has a lower temperature than the nail, it actually has more heat than the nail does. So the nail's at a much higher temperature because the average kinetic energy of the particles is much higher, it's hotter. But because it's only a very small nail, there isn't actually the total sum of it isn't very big. Whereas in the lukewarm bath, while it might be lukewarm, therefore the temperature is much lower, there's a lot more particles present in this system. And so therefore the sum of just the energies would be greater. And so if we had this lukewarm bath and we had this red hot nail, if I put the red hot nail into the lukewarm bath, well, we said that heat always flows from high to low temperature, and so the heat would flow from the nail to the lukewarm bath, even though technically the lukewarm bath has more heat than the red hot nail. And there's no instrument that actually measures heat directly. For temperature, we can measure it with a thermometer, but there's no instrument that measures heat directly, and so that's why we have to talk about an enthalpy change. We'll never hear just an enthalpy of a reaction, it's always the enthalpy change, because we have to measure a change between the reactants and the products. So then how do we go about measuring enthalpy changes? So to measure the enthalpy change, we have to arrange for the heat energy to be transferred into a particular mass of a substance. So let's say we're doing an exothermic reaction. We know that our system loses heat energy, and it gives that heat energy out to the surroundings. And so what we can arrange for is that heat energy gets transferred into a particular substance, often water, and we have to know the mass of that substance that we're transferring the heat into. And the reason for that is, again, because the amount of the substance depends on, therefore, on the enthalpy change. And so we have to know the mass of the substance that is being heated or cooled, the temperature change, which we can measure with a thermometer, and the specific heat capacity of the substance that the heat is being transferred to. Now, the specific heat capacity is given the symbol a lowercase c. It's the amount of heat needed to raise the temperature of 1 gram of a substance by 1 Kelvin without change of state. Essentially, if I have a particular substance, how much energy does it take for me to raise the temperature by 1 Kelvin and for 1 gram of that material? So 1 gram of the material raised by 1 Kelvin without changing its state, so without melting it or without boiling it, for example. How much energy do I need to do that? Now, the key thing is everything here relates to the surroundings, not the actual system. So let's say we have an exothermic reaction. Our system is the actual chemical reactants that we are dealing with. Let's say it's a neutralization reaction. It's the HCl and the NaOH. Our surroundings, though, is everything else. So the surroundings is the water that we're doing the reaction in. It's the polystyrene cup we're doing the reaction in. And so this is why it's so important that we have to consider what the surroundings are in this case. Let's say in this example I've just talked about here, we're transferring this heat energy into the water. So we have to know the mass of the water that we have, the temperature change that we measure of the water, and the specific heat capacity of the substance the heat's being transferred to, again, the water. And so the equation that we can then calculate this from is that the heat change, the energy change, now note that this isn't an enthalpy change, this is actually a heat change, so just an energy change. We take the mass of the heated substance, we multiply it by the specific heat capacity of that heated substance, and we times it by the temperature change of the heated substance. Now, the really key thing with this equation, and one really key error that I see lots of people making, is that typically they will give you in a question the masses of the reactants that you've used. So let's say that we've done this neutralization reaction of HCl plus NaOH. They will give you essentially maybe the concentration of those reactants and the volumes. But what we're interested in is the mass of the heated substance. So it's the mass of the water in this case that we're interested in. Everything in that equation refers to the heated substance. So not the actual chemical reaction going on, but the substance you're either transferring the heat into or out of. And so the heat change is the mass of the heated substance multiplied by the specific heat capacity, which is of the heated substance, times the temperature change of the heated substance. And we can also write it out in symbols. So we have Q for a heat change, M stands for mass, the lowercase c stands for specific heat capacity, and delta T stands for a change in temperature. And there has to be some specific units for this. So we have our mass is in grams, the temperature in Kelvin, could also be in degrees Celsius as well, because given it's a change in temperature, the Celsius and Kelvin scales are on the same. If you increase it by 1 Kelvin, that's the same as increasing by 1 degree Celsius. So because we're dealing with a change, it doesn't necessarily matter whether we're given them in degrees Celsius or Kelvin, but really technically it should be in Kelvin. And then the specific heat capacity is given the units of joules per grams per Kelvin. And hopefully you can see if you times all of those things together, your grams and your kelvins cancel out and you're just left with joules. So your heat change is measured in joules. So once we've calculated our heat change, Q, which of course relates to the surroundings, remember that enthalpy change is measured in kilojoules per mole. So what we just calculated on the previous slide is our heat change, simply just the joule components of that, or the kilojoule if you divide by 1,000. Enthalpy change is kilojoules per mole, so we have to also have a mole component. And so to find the enthalpy change, we need to work out not only the heat change, but also the moles. And this is where it's a really important distinction here between the system and the surroundings. On the previous slide, we've calculated the heat change, but we've calculated the heat change for the surroundings. In the example of the neutralization, the system is our HCl and our NaOH. The water in the polystyrene cup is the surroundings. That's what we transfer our heat energy to. And so we can calculate this heat change of the surroundings by measuring the temperature of the water, the change of that temperature. But when we need to work out the moles, enthalpy change is of the system, of the actual reactants. And so we have to work out the moles of the system, so the moles of the NaOH and the HCl in this case. But the heat change was calculated for the surroundings, the water. Now the reason why we can do this is because we can't measure the heat change for that system very easily, but we can measure the heat change for the surroundings easily. And of course we know that energy can't be created or destroyed. That's our first principle of thermodynamics. And so the heat change that the heat that we've given out from our system to the surroundings, essentially the number will be the same, it's just the sign of that change that is different. The amount of heat that the surroundings will have gained will be exactly the same as the amount of heat that the system will have lost. And so the heat change of the surroundings is the same as the heat change of the system. And so we work out our moles of the system either by using that the moles is the mass divided by the MR, the mass divided by the molecular mass, or using moles is equal to concentration times volume if we have a solution-based problem. So once we have both of these quantities, we divide our heat change, which was of the surrounding, technically Q in kilojoules, by the moles, which is of the system, which is in moles. And this gives us the enthalpy change for the reactions. This is why it's really important, as I said on the last slide and kept hammering it home, that when we use our Q equals mc delta T equation, that we're not dealing with the actual system. So quite often questions will give you the mass of the reactants that are being burnt, for example, or used in the reaction. It will also then give you the mass of water or whatever the substance is that's being heated up and the specific heat capacity of that substance that's being heated. And so the Q equals mc delta T equation always refers to the surroundings, the thing that we are heating up, not the system. The moles equations relate to the system, so whatever the actual chemical reactants are. And so our enthalpy change, remember in kilojoules per mole, is simply the heat in kilojoules divided by the moles in mole. And the only really key thing is that we always have to consider whether the reaction is endo or exothermic. So if we know that it's an exothermic reaction, we have to include a negative sign, because just by doing this calculation of Q divided by N, we'll always have a positive number. And so we then need to work out, well, is our enthalpy change exothermic? In which case it's a negative enthalpy change, so we put a negative sign in front of it. Remember, this is examples like combustion, if it maybe burns something, or a neutralization reaction. Or if it's an endothermic reaction with taken heat energy in, it's a positive enthalpy change, we don't have to change the sign. So always consider if it's an exothermic or endothermic reaction. And I always used to, if it's an exothermic reaction, always simply write at the top and the bottom of the page in big writing that it's an exothermic reaction. So that will remind you to make sure that you put a negative sign on your answer, because quite often that's a big error that people make and lose very silly marks for getting the right answer, just not putting the correct sign in front of that enthalpy change. Now, measuring the change in energy in a chemical reaction is something called calorimetry. And we can use a calorimeter to find enthalpy changes. For example, if we're trying to find the enthalpy change when a neutralization reaction occurs, or when a fuel burns, for example, in a combustion reaction. And so typically the way we do this is the way that I've been kind of alluding to as we've gone through here. We measure the temperature change of a known mass of water. And so one of the assumptions for this is that we are assuming that, let's say it's an exothermic reaction, we have all of our heat energy from the system being given out. It gets given out to the surroundings, and what we're going to assume is that all of this heat gets transferred to the water. And so a really simple calorimeter, I've been talking about doing it in a sort of polystyrene cup. And so here we have this kind of coffee cup calorimeter. And so you have your actual sort of styrofoam cup. Key thing here is that styrofoam doesn't conduct heat. It's an insulator. You don't want your heat to be able to escape out, and therefore you can't measure it. You wouldn't measure all the actual true energy change. If the heat could be transferred out of the water, you want it to stay within the water, so you can measure the energy change of that. And so we have this insulating material, typically some kind of cover on the top as well to insulate. So we don't, obviously if there's no cover on the top, there's a very large hole at the top that heat can escape out from. And typically we poke two holes in this. So the first has a hole for a thermometer, so we can measure the temperature change, and that relates to the heat change. And the second is that we have often a space to put a stirrer in so that we can stir the solution with, because we want to make sure that our heat energy isn't just localized over to maybe one side of that cup. We want to make sure that the heat energy is completely dissipated evenly throughout our surroundings, in this case the water. Now, although these polystyrene cups are fairly good insulators, what we mean by having a good insulator is that they have a low specific heat capacity. Some of the heat will still be lost from the sides and from the top. They're not perfect insulators. They will lose some heat from the top and the sides. And so what that means is that we do lose some heat. And then what this actually means is that we get an inaccurate enthalpy change value, because technically more heat has been given out than we have calculated. The temperature change would have probably been slightly higher than what we're actually seeing on the thermometer. But this can be slightly allowed for by plotting something called a cooling curve, which we'll see on the next slide. There are also lots of other factors that can come into play for heat loss as well. So typically what you do to maybe even do further insulation is that you put the polystyrene cup inside a beaker. But we've assumed, as we said on the previous slide, that all of our heat energy that gets released out to the surroundings, or all of the heat energy that's taken from the surroundings, if it was an endothermic reaction, comes from or to the water. But let's say energy has been given out. What's to stop that energy not getting absorbed by the water, but also getting absorbed by the beaker or by the polystyrene cup? And so these other materials can also get heated rather than the substance that we're measuring the heat change of. And so not all of the heat energy actually reaches the water that we want. Another example is if we're using a fuel to burn the substance. If we're doing a combustion change here and we're using a fuel to burn the substance, it could be actually that we get incomplete combustion. And therefore we're not having it's not being completely burnt in oxygen. That goes back to our definition again of that enthalpy change of combustion. We have this idea of when it's completely burnt in oxygen. If there's incomplete combustion, there's not enough oxygen. And so if we're using this kind of coffee cup calorimeter type example, you can put a lid on the top, you can put lots and lots of further insulation, maybe multiple polystyrene cups inside each other, or that inside a beaker. And these will reduce these errors with heat loss. You can ensure complete combustion, so a really plentiful supply of oxygen. And you can also introduce a conductor as well that will transfer the heat to the substance that's being heated. So putting a conductor in there allows you to really well transfer the heat from the system to whatever substance it is that we are measuring the temperature change of. Another example might be if you're trying to burn something, rather than just burning it in air, using a supply of pure oxygen. And so that's going back again to this idea that you don't want incomplete combustion, you want complete combustion. So I said that one of the ways to account for this heat loss out of the top and out of the sides of our calorimeter is to plot a cooling curve. And this is an example of a cooling curve on this slide here. And so the way that we plot this is we have our y-axis as the temperature that we measure. We measure that with a thermometer. And on the x-axis, the time. And so when we do this experiment, let's say we have our polystyrene cup, we have our reactants in there. What we tend to do is we tend to just leave our reactants in there for a few minutes. And this is just to make sure that they are at room temperature, that they're at the same temperature and that they're at a steady temperature, which will be the temperature of the room that we're at, so say 25 degrees. And so we're going to measure the temperature of our solution. Remember that we're measuring actually the temperature of the surroundings, really. So we want to make sure that that's sort of equilibrated, that it's at a constant temperature. So I'm going to measure the temperature change every 30 seconds. And you can see that this happens up until 3.5 minutes. Then on 4 minutes, what we're going to do is actually, let's say we have, when we add two reactants together, this is what produces our change. We're going to add our two reactants together directly on the 4th minute. Now, as we do that, we don't measure a temperature change. The next time, a temperature value, sorry. The next time we're going to measure our temperature with the thermometer will be at 4.5 minutes. So we leave our solution to just kind of equilibrate to a constant room temperature. On the 4th minute, it doesn't have to be the 4th minute, it can be whatever minute you decide to do. It's good to leave it for 2 or 3 minutes though, just to make sure that it's at the right temperature. So at a specific time, mix the two reactants together, and then sort of 30 seconds later, however long your increments are, you then measure the temperature again. And so you can see from 4.5 minutes all the way down there to kind of 10 minutes, I've then measured what the temperature of the solution is, of the water in this case. And so you can see that actually what happens is we get a temperature rise when we mix. And generally, as we go down from kind of 4.5 minutes all the way down to 10 minutes, generally we get this slow cooling of our products. So we had our reactants temperature that we remained steady, mix it on 4 minutes, then measure it every half minute from there on, and we get this generally slow cooling of the products. And the way that we simply do this is we simply draw a line through all of the points. So the green kind of curve that you can see is the actual cooling curve. What you need to draw are these two red lines that you see. And so what we're going to do, essentially, they're lines of best fit through the points. And so we have a line that essentially is just a straight line, a straight horizontal line at the bottom. That's our steady temperature of our reactants. We're then going to have this sort of diagonal line at the top. So we're just going to draw a line through those crosses that represent the temperature of the products. And the key thing is that we don't just draw it to where the crosses end, but that we extrapolate, we go further than that. So we're going to draw these lines extending back further than we need to, and also forward further than we need to. And what this means is that we're going to end up with a portion around the 4 minute mark where these lines overlap. And so then all we're going to do is draw a very sort of vertical arrow, if you like, between where the red line is at the bottom on 4 minutes and where the red line is at the top on 4 minutes. And so what this essentially is telling us is, well, okay, that's the temperature we started at the bottom red line. The top red line is telling us essentially what the temperature of that product would have been at exactly 4 minutes, as we measure it exactly on 4 minutes, before we've lost any heat change to the surroundings and to for example, to the polystyrene cup or at the top of it. And so the key thing is to plot all these temperature points and then to extrapolate backwards and to extrapolate forwards on the various lines that we draw, so that we can actually find temperature rise on mixing, so what that actual temperature change was the instant we mix those two reactants, and it's just the difference between the two temperature values that we've got from those extrapolated lines. So, time to have a go at some questions. Here we have some calculation questions on working out heat changes and enthalpy changes. So if you want to have a go, pause the video and the answers will be on the next slide. So the first question here then, we had a 0.74 grams of propane being burnt, essentially this is a combustion reaction. And this propane was burnt and it was used to heat water. So already here we're given what the system and what the surroundings is. Our system is the propane that we're burning. The surroundings is the water. We were told the temperature was increased by 8 degrees. 100 grams of water was heated. We're given the specific heat capacity for water and to calculate the enthalpy change. So remember that we have to calculate an enthalpy change. It's kilojoules per mole. So we have to have a kilojoule part, the heat part, and we have to have a mole part, which is the moles. And so we can say that our enthalpy change is Q divided by N, the heat divided by the moles. Remember that the heat refers to the surroundings, the N, the moles, refers to the system. And our two equations that we need here is that the moles, because this is a solid mole question, we're going to have that the moles is mass over mR, mass over the molecular mass. We can work this out, so 0.74 grams of the propane divided by the molecular mass of the propane. Remember, to calculate a molecular mass, we just add together all of the atomic masses of all the elements involved. Propane is CH3, CH2, CH3. That's 44.0 as a molecular mass. Remember that atomic masses and molecular masses are always given to one decimal place. And so 0.74 divided by 44.0 gives you 0.0168 moles. The other equation is the heat equation. So heat is equal to the mass times the specific heat capacity times the temperature. So Q equals mc delta T. We have our mass of water that we're heated. That's 100 grams. Now sometimes, especially for water, they will give you the volume of water that you've used. The little trick and the cheat that we use here is that the density of water is 1 gram per centimetre cubed, or 1 gram per milliliter. And so what that means essentially is that we can just directly use whatever volume we have as a mass. So 100 centimetres cubed of water is the same as 100 grams of water. Or 50 millilitres of water is the same as 50 grams of water. So essentially we can just use the same number. because we've used that density trick. The density is 1 gram per centimetre cubed, and therefore the numbers essentially are the same. So we have our mass here, 100 grams. It's always, remember, the thing that we've heated, the surroundings, the water in this case, so 100 grams of water multiplied by the specific heat capacity of water, 4.18, and then multiplied by the temperature change of the water, which we were told was 8 degrees Celsius. If you remember back on the slide where I gave this equation, I said that really temperature typically is in Kelvin. Because it's a temperature change, it doesn't matter whether it's in Kelvin or degrees, because the change is the same for both of those scales. An 8 degree Celsius change is the same as an 8 Kelvin change. But remember that the heat equation always refers to the thing that we are heating, the surroundings that we're heating. Another way to just double check it is to always, they'll give you what the specific heat capacity is. The specific heat capacity was for water, and therefore everything in this equation has to be for water. It's the mass of the water, not the mass of the propane, and also the temperature rise of the water. And so we do this calculation, we get 3,344 joules, or because typically these are big numbers and enthalpy is of course in kilojoules per mole, typically I always convert to kilojoules, and so therefore it's 3.344 kilojoules. And so then simply to work out our enthalpy, remember it's Q divided by N, so we put these numbers in and we end up with 198.8 kilojoules per mole. Now, remember, as I said a few slides ago, the really key thing to remember is to note whether the reaction you're looking at is exothermic or endothermic. Here we have a combustion reaction. We're burning this propane, so that's an exothermic reaction. Exothermic reactions have a negative delta H, and therefore we have to make sure that we put a negative in front of that. So our answer would be negative 198.8 kilojoules per mole. The second question was we were told we had 50 centimetres cubed of a 2 mole per decimetre cubed sodium hydroxide solution and 50 centimetres cubed of a 1 mole per decimetre cubed hydrochloric acid solution were mixed in a polystyrene cup. The temperature rose by 11 Kelvin, and to calculate the enthalpy change and comment on the value obtained. So we have to do exactly the same calculation that we've just done in our previous question. Again, we need to have a mole component and we need to have a heat component. The heat component refers to the water, the surroundings that we've heated up in the polystyrene cup. The mole refers to the actual chemical system, so this is our actual reagents here. Now the key thing to note is that we've added 50 centimetres cubed and 50 centimetres cubed together of our two reagents. And so the total volume of our solution is 100 centimetres cubed. Again, this is another key error I see a lot of people making, that they just use one of those 50 centimetre cubed volumes. The true volume, think about it actually doing this experiment, you would add the two together, the total volume is just the sum of the individual volumes. So the total volume of liquid that you'd have in the polystyrene cup is 100 centimetres cubed. And because these are aqueous solutions, essentially we can make the assumption that it's 100 centimetres cubed of water. And again, we're going to use this trick of the density of water being 1 gram per centimetre cubed. So 100 centimetres cubed is the same as 100 grams of water. So to work out Q, we have our mass of the water, which is 100 grams. Again, it's all for the thing that is being heated, the thing that the energy is being transferred into. This is the water, multiplied by the specific heat capacity of the water, and multiplied by the temperature change of the water. And we were told here that temperature change was 11 Kelvin, so we can just put 11 in. And we end up, once we've divided by 1,000 to put it in kilojoules, 4.598 kilojoules. Then we need to work out the moles. This one isn't quite so simple as the one before. Here we have a solution-based mole problem, so we have to use that moles is equal to concentration times volume. However, we need to work out the moles of both of our reagents, because one of them will be the limiting reagent. Remember that the limiting reagent is the one that has the smallest moles. If you're not quite comfortable with this idea, you can go and look at my set of videos on these calculation type questions. But our limiting reagent is the one that limits how much product we can get. It's the smallest, the thing that's present in the smallest amount, and therefore it limits how much product we can get. It's the one with the smallest moles. And so the moles of the acid is the concentration, 1 mole per decimetre cubed, multiplied by the volume, 50 centimetres cubed. And again, if you're not happy with these unit conversions, go back to my videos on concentrations and these calculations. We have to make sure our units match, so 1 mole per decimetre cubed doesn't match with centimetres cubed. And so the easiest way to convert is to convert the centimetres cubed volume into decimetres cubed. We do this by dividing by 1,000, so it essentially becomes N is C times V divided by 1,000. Do that calculation, we have 0.05 moles. Do the same thing for the alkali, and we end up with 0.1 mole. And so the smallest amount here is our acid, 0.05 moles. And that's the one we use. That's our limiting reagent. Essentially, we're going to end up with some alkali being in excess and being unreacted. So therefore, we now have our moles of the actual system, the acid and the alkali. We have our heat change Q of the surroundings of the water that we've heated up. We put these values in, and we end up with an enthalpy change here of 92.0 kilojoules per mole. But again, remember, this is a neutralization reaction, and therefore it's exothermic, and so we have to have a negative enthalpy change. So the answer would be delta H is equal to negative 92.0 kilojoules per mole. Again, always note significant figures. So the smallest number of significant figures we were given in the question was 3, for example, the 11.0 Kelvin. And therefore we give our answer to 3 significant figures, 92.0. And because it's exothermic, negative. And it asks you to comment on the value you obtain. You just say that it's a negative value because it's an exothermic reaction, because heat has been given out from the system to the surroundings. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found it useful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.